Hello everyone. So we will now have a remote research paper by Michael Wessel on an ontology-based dialogue management framework for virtual personal assistants in Common Lisp.
ELS presentation. My name is Michael Wessel. I'm an advanced computer scientist in the Artificial Intelligence Center at SRI International in Menlo Park, California. And this is about an ontology-based dialogue management framework for virtual personal assistants in Common Lisp. So here's the agenda of my talk. I'm going to tell you a tale of 4 different representations for virtual personal assistants, or digital personal assistants, as some folks prefer to say, in and with Common Lisp. I'll use VPA for short in the following for virtual personal assistant. First, I'll talk a bit about our VPA background at SRI and also prepare the stage by showing a little demo video of a simple ontology-based VPA to illustrate basic dialogue management capabilities, and later explain how ontologies can be used to realize these capabilities. The main focus of this work is on ontology-based dialogue management, which is the central component of a VPA. Basically, that's the brains of the VPA. Then we talk about the different VPA development phases we went through, the challenges we encountered, and the different representation layers that addressed these challenges. And again, this is really only about dialogue management. The pinnacle of this work is a set of Common Lisp macros, a domain-specific language DSL, our dialogue specification language DSL. So if I had been more witty, I had called this DSL squared or something like that. I said VPAs in and with Common Lisp, and it will become clear during the talk what I mean with that. My employer, SRI International, has a rich history in interactive computing. You might know that this is a place where Doug Engelbart invented the computer mouse in 1964, which was then famously featured in the mother of all demos in 1968, and more recently, the SRI spin-off Siri was acquired by Apple in 2010. VPAs are becoming more important these days because they allow us to interact with and use computers in the most natural way for humans, using natural language. And in certain situations, this might be the only input-output modality that can be used, for example, whilst driving the car, etc. SRI didn't stop working on VPAs after Siri. We wanted to explore the idea if we could make VPAs even smarter by adding more sophisticated natural language understanding and contextual sense-making by means of description logic and OWL reasoning to the dialogue manager. One example is anaphora resolution. For example, in a dialogue with a restaurant recommendation VPA, a number of restaurants might have been suggested by the system, say, a pizza place and a Japanese restaurant. If the user then asks, what is the address of the restaurant, then this is ambiguous, as it might refer to either of the suggested restaurants. If, however, the question was, what is the address of the Asian restaurant, then from the context it is clear that this should only refer to the Japanese restaurant, but not the pizza place. Ontologies and a rich semantic representation of the discourse can be used to implement capabilities such as these. We hence started using Lisp and the Racer description logic and OWL reasoner to implement an ontology-based dialogue manager, fully in Lisp. This is the first prototype, level 0. This started in 2015. The terminological component, or T-box of the VPA, contains classes and relationships, both for the domain model and for discourse representation. The A-box contains the actual instances of these classes, including domain model instances, such as restaurants, as well as the actual runtime representation of the dialogue, the so-called dialogue graph or dialogue A-box. The runtime dynamics are implemented by means of ontology-based rules, computing the VPA's responses. These rules assess the current dialogue A-box and then simply figure out what to say next. We will present more details later, but first let's have a look at the demo video. Here is the demo video of the Onto VPA system in 2016. It demonstrates semantic search, semantic similarity, anaphora resolution, the use of hypernyms and synonyms, the ability to refer to previous dialogue entities, contextual interpretation of arbitrary input, and disambiguation. Hello.
Hi, what can I do for you?
Is there a Chinese restaurant in Menlo Park?
Sorry, I didn't find any such Chinese restaurant in Menlo Park. Do you want me to generalize the query?
Yes, please.
The next best option to a Chinese restaurant in Menlo Park is the Gombe Japanese restaurant at 1438 El Camino Real, Menlo Park at 1.11 miles.
Is there a bookstore close to the restaurant?
The bookstore closest to the Gombe Japanese restaurant at 1438 El Camino Real, Menlo Park is the Kepler's Books at 1010 El Camino Real, Menlo Park at 0.71 miles.
Can you show the library on the map?
Sorry, but I can't recall that we have talked about any library. How can I help you now?
Is there a pizzeria?
I suggest the Applewood Pizza Restaurant at 1001 El Camino Real, Menlo Park at 76 miles, which is a pizza place.
Palo Alto.
I suggest the Olive Garden Italian Restaurant at 2515 El Camino Real, Palo Alto at 459 miles, which is a pizza place in Palo Alto.
Is there a cafe close to the restaurant?
Do you mean the Gombe Japanese Restaurant at 1438 El Camino Real, Menlo Park?
Yes.
Sorry, I didn't find any cafe close to Gombe Japanese Restaurant at 1438 El Camino Real, Menlo Park. Do you want me to increase the search radius? Search radius was 3.0 miles.
Yes.
I suggest the Cafe Baroni at 1010 El Camino Real, Menlo Park at 0.71 miles, which is a cafe.
Is there a bookstore close to the Asian restaurant?
The bookstore closest to the Gombe Japanese Restaurant at 1438 El Camino Real, Menlo Park is the
Thank you.
The pleasure was mine.
This slide shows the architecture of the OntoVPA system. From left to right, the processing pipeline goes as follows. First, automatic speech recognition, or ASR, translates the speech waveform into text. Here, find me a Chinese restaurant in Menlo Park. Next, a classifier is determining the intent behind that utterance. Here, the find POI intent, find point of interest intent, is being recognized. The intent class is defined in the ontology, and an intent instance of the find POI intent class is instantiated in the dialog A box. The slot filler is then introspecting the definition of the find POI intent class and figures out which parts of the input should become slot values of the instantiated intent. This is the job of the ontology-based slot filler. The find POI intent class has a slot dialog entity, which is now instantiated with the Chinese restaurant instance, which again has a slot value for the in-city slot, which in turn is filled with the ontology instance Menlo Park. Menlo Park is a city instance from the domain model A box. Then the ruler engine assesses the current state of the dialog A box and computes the response. It retrieves a matching restaurant instance. The computed VPA answer is also represented in the dialog A box so that the system has a full recollection of the dialog of both the users as well as the system's turns. Then TTS, or text-to-speech, will generate voice output, but the system is also multimodal and can produce other output modalities as well. The next slide shows that all of these components are part of OntoVPA. The dialog runtime representation happens in the A box, and the background and domain knowledge, the ontologies, are supplied as T-boxes to the system. And then the rules compute the system responses. Our first VPA ontologies were very simple, here in native Racer syntax. By the way, if you're interested in Racer, the OWL and description logic reasoner implemented in Common Lisp, you can get it from GitHub these days. It is open source under a BSD3 license. So we started with just a handful of top-level classes such as entity, event, and intent. Moreover, some relations were defined so that we could construct the dialog graph at runtime. For example, previous intent, linking together the dialog steps in the dialog A box. Moreover, some domain-specific relations such as the POI relation was defined, linking intents with their POIs, as well as the city relation, giving the POIs their city attribute slot value. And then we had a couple of POI subclasses for restaurant types. Even such a simple ontology provided some new VPA capabilities, namely a notion of semantic similarity for search. Using the taxonomic distance, we can, for example, see that a Chinese restaurant is more similar to a Japanese restaurant than, say, McDonald's. And also this taxonomy then allows us to deal with hypernyms and so forth, as illustrated in the demo video. Once we have instances in the A-box, we can use Razor's A-box query language to retrieve them using ontology-based queries. Here on the left we have a number of POI instances. For example, POI 106 is a bar as well as an Indian restaurant, and there's a city relation. It's related to the city Palo Alto. It is in the city Palo Alto, and Palo Alto is an instance of the city class again, which is defined in the ontology. Now the idea of ontology-based queries is that you can use the vocabulary defined in the ontology, such as Indian restaurant or city relation, right, to retrieve those instances from the ontology. And note that membership of the retrieved individuals does not need to be stated explicitly, but it could be the case that membership in these classes and relationships is inferred from the axioms in the ontology. After we have seen how the A-box is used to represent domain instances, such as the various restaurants, and how we can use ontology-based queries to retrieve them, let me also show you the dialog A-box in more detail. Above this solid line here, we have the VPA utterances or system turns, and below we have the user's utterances, user intents or user turns. VPA makes the first move by instantiating a greeting response. Hello, what can I do for you? Next, the find POI intent is instantiated together with its requested Japanese restaurant in the city Menlo Park. And note that this structure here, Japanese restaurant directly inside Menlo Park, basically acts as a query by example specification. At that point, control is passed to the dialog manager, which is now assessing the current state of the dialog A-box. Similar to a blackboard architecture, a number of ontology-based daemon rules that implement different possible responses are now evaluated and checked for applicability. Such a rule has an ontology-based A-box query as its precondition, as just illustrated, but can then augment the A-box with its conclusion, similar to a production rule when it fires. Conflict resolution is performed based on rule preferences and defeasibility, and one of these rules is executed. This rule then computes the response and asserts its conclusions into the dialog A-box, as shown in the next slide. Here, a find POI system response has been computed, and the retrieved matching restaurant instance POI 152 is also included in the result structure. When the user now says, "Can you show it on the map?" instantiating a show on map intent, yet another rule is being executed, and show on map system response is being asserted. Now, the rule that executes show on map knows that it refers to the last presented dialog entity, in this case the Japanese restaurant POI 152. And note that we are also asserting bookkeeping relations such as previous step and previous answer, so that we can traverse and navigate through the full dialog A-box, the full discourse history. The daemon rules can become quite complex though. A rule with the ID find POI same city perfect match is shown here. It computes the answer to a find POI intent in case the restaurant type as well as the city as well as an additional near to constraint are specified. Say you want a Chinese restaurant in Palo Alto near to the train station. The POIs satisfying these constraints are actually computed in the conclusion of this rule using a lambda expression. The lambda expressions gets the intent X, the city C, as well as the query by example POI as arguments. With these bindings in place, inside the lambda, another query find POI same city perfect match is evaluated to retrieve the matching POIs from the A-box. Now, if matching POIs have been found, a result as expression is constructed and asserted into the dialog A-box describing the response. If, however, no matching instances have been found, then the rule computes the follow-up requests and asks the user, "Do you want me to relax your query semantically?" Meaning, do you want me to generalize the query? Now, based on the user's answer to this question, a follow-up continuation is being executed. In case of yes, a find POI same city imperfect match follow-up rule is being executed, else just a generic greeting message follow-up. And the remaining definitions are shown here. The query that retrieves the matching POI instances from the A-box is shown at the bottom here, and it uses a lambda atom to evaluate whether the currently considered candidate A-box instance Z is satisfying the constraints specified on the query by example PUI from the request, which here is simply the case if the types found on Z are a superset of the types of Y. So a Chinese restaurant would be a match for a restaurant, since Chinese restaurants are also restaurants, right? So we have a superset relationship. For a first level 0 prototype developed in about 2 weeks, that wasn't too bad. However, there were a number of shortcomings. First, the performance wasn't too great, and a tighter integration with the Java-based components, ASR, classifier, slot filler, and output presentation was desirable. Moreover, our prototype lacked generality. The classes and rules were too domain-specific, and unlike the dialog manager, couldn't be reused easily for future projects. Also, management was keen on incorporating off-the-shelf ontologies to reduce cost, but wasn't too convinced of Lisp in this context either. This then led me to embrace OWL, the web ontology language, and Sparkle for OntoVPA, so that we could put the W3 standards label on our product. Off-the-shelf ontologies exist in these standard formats, and Racer is capable of reading, processing, and writing OWL as well. Moreover, we decided to invest in upper-level abstractions by creating a fine-grained upper-level dialog management ontology. Whereas previously we only had intent and response classes, really, we now had a sophisticated SpeechAct-inspired set of dialog management classes for requests, responses, user turns, system turns, answers, intents, etc. I decided to do the OWL importing, ontology blending and modeling in Racer, but then use the Gina, OWL and Sparkle reasoner implemented in Java at runtime to address the tighter integration with Java and performance points. The OntoVPA compiler ingests the imported, specialized and extended ontologies together with our domain-specific ontologies and creates an all-in-one lightweight runtime version of that ontology. This single lightweight ontology is then used at runtime by Gina for OWL runtime reasoning and for ontology-based Sparkle query answering. To achieve this, the compiler materializes inferences so that OWL inference is mostly reduced to slot value lookups at runtime in Gina, which is very fast. However, Sparkle is not a rule language, but a query language. So in order to use Sparkle rules as daemon rules, as we did before, I implemented a rule engine with Gina in Java. Rules are extended Sparkle queries. Everything was designed to be generic on an upper level and reusable. For example, previously checking for a required slot was a job of a domain-specific rule. But here we implemented a generic dialog management rule that would work in a generic way, and for all intents that would define a required slot. To satisfy the let's use off-the-shelf ontologies to reduce modeling costs desire, I imported and extended schema.org. Schema.org has a restaurant class with many useful slots, and many other useful classes that made sense for our point of interest demo VPA. Part of our upper-level dialog management ontology is shown here. You see that we have classes for requests and responses from the user and the system side, and that there are generic classes such as generalize, attribute value, user request. This could be used to generalize, for example, the restaurant type from Chinese restaurant to Asian restaurant, like in the demo video. In the dialog ontology, we tried to maximize inheritance and reuse, resulting in a deeply nested class hierarchy. For example, the upper-level intent, search source entity intent, is defined to retrieve any source entity from a data source, from the A box. It specifies a query by example dialog entity slot value, and the idea is that a more specialized version of this intent, search PUI schema.org intent, restricts the dialog entities to instances of PUI. This covariant range specialization of inherited dialog slots is used as a frequent ontology modeling pattern. So rather than accepting generic entities as query by examples, we now require a point of interest entity from schema.org, like a restaurant, for the search PUI schema.org intent. In order to provide generic dialog management rules, we needed some more expressivity. Consider a rule that inquires for a missing required slot value, for example, if the restaurant type or cuisine is missing from the request. Instead of writing a domain-specific rule, determine missing restaurant type system request, we can have a generic determine missing slot value system request rule. This rule would need to introspect the definition of the current intent and figure out which required slots are missing. This requires quantification over relations, or slots, which is basically a form of second-order quantification. Sparkle provides this, since variables can be used at class and slot position. I'll show an example later. Such a Sparkle rule would need to know which slots are required and which are optional for each class. The Ontology-VPA compiler makes this information explicit, as shown on this slide. Here's a Sparkle rule that identifies and flags all required but still missing parameters on the current request x. By looking at the asserted type t of x and the required parameters which are declared on a class level for t, it identifies all parameters, all slots y, which are not yet found on x. So if x does not have a slot value for y yet, then x, the request, is marked as incomplete, and also the missing required parameter is flagged. So a follow-up rule can then inquire the user to specify the missing required parameter for x. The high expressivity of Sparkle and ability to quantify over properties or slots and classes also allows us to now implement logic in Sparkle for which we required Lisp predicates within lambda atoms previously. For example, for the POI retrieval query, we need to check that the types on the matching POIs are a superset of the types specified on the query by example point of interest. Using Sparkle, we can now basically do a second-order quantification over all the properties and check that the candidates have at least the properties that the query by example POI specifies. This includes the type property as well. With level 1 in place, why didn't we stop there? Why did we have to go to level 2? Well, we encountered some more challenges. First, there were also some severe reservations concerning the use of OWL in Sparkle. The hope that customers would use OWL in Sparkle was a bit, well, let's say, over-optimistic, and the solution also seemed to be much too complicated for the customer. Hence, a simplified modeling style was required. This is when we adopted a conceptually much easier model, dialog workflow graphs. Customers could then define their own dialog workflow graphs using node and edge types that we had defined in the upper level, and for which we had also implemented a dialog workflow graph interpreter, again using Ontology-VPA's Sparkle rules. So this was a simplified modeling layer on top of level 1. The benefits: no more OWL modeling, no more Sparkle modeling, but with additional complexity for us, the upper level developers. An example of a dialog workflow graph is given here. It describes a radio repair diagnosis workflow. Starting with the question, do you hear a sound and your radio is mute? It then walks you through a dialog to figure out what's wrong with your radio and what you can do to fix it. For example, it asks if the power LED is lit, etc. It eventually comes up with a solution, for example, plug in the power cord. My claim is that this representation is intuitively understandable. Different nodes represent different kinds of workflow actions, like asking a question or asking the user to perform some action. Some of these nodes would also update internal data structures in the A-box to manage the state. The idea then was that we, SRI, would define the upper level vocabulary to instantiate these workflow graphs and also provide the interpreter rules such that the customer could directly instantiate and use these workflow graphs. Now, in terms of modeling, the customer would then use Lisp instance and related macros to basically construct the graph to create the labeled nodes and edges as shown here. But of course, it's also conceivable that we would have developed a graphical editor to support this. At runtime, this dialog workflow graph is now interpreted by a set of Sparkle workflow graph interpreter rules that we had defined. There's also still the dialog A-box in addition, so two graphs are now being traversed and updated during the dialog by these interpreter rules. But this is invisible to the customer. So, good news! Customers were able to change and extend workflow graphs. However, it was conceived as being too laborious and also a bit error-prone because of long symbol names, and we didn't have any checks that could identify dangling links based on misspellings and so on. Overall, modeling took too long and now was on a level of abstraction that was too low. Also, the additional control vocabulary required for setting up yes, no branching, etc. was causing a bit of a boilerplate representation problem, and the control vocabulary was also alien to the terminology of the domain. it is always preferable to speak the language of the customer. The challenge then was, how can we make that more convenient and have better abstractions? This led to the creation of our final level 3, the dialog specification language DSL. DSL can be changed flexibly and also does error checking to prevent dangling links, etc. Moreover, visual representations are now generated automatically, and this facilitates communication about these models as well as participation. And this is how DSL looks like using an excerpt from our MEDIC VPA system. It's just a node macro. The system utterance is specified and then the node ID. And then followed by a number of clauses that represent the outgoing edges or transitions of the node. Here, the node is asking for the location of the bleeding. Where's the bleeding? And depending on the user's answer, the system then transitions into the subgraph for limb treatment or for head or neck treatment. Note that there is still a domain-specific ontology behind. For example, body parts, limbs, head or neck, etc. are all classes in the MEDIC ontology. Let's assume the user answered the question by replying, the bleeding is in the face, right? And then due to the ontology, the system will realize that face is subsumed by head or neck, so it should transition into this successor node here, the head or neck treatment node. But before doing this, it uses the extract and store clause here to first identify all parts in the input which are subsumed by the body part concept, right? So in this case, this would be face, right? And then face would be stored as a slot value on the slot hemorrhage location on the current user individual in the A box. That way we are keeping track of acquired information during the dialogue by putting arbitrary parts extracted from the input, right, using ontology expressions into the user profile individual in the A box. Now that we have stored away the face hemorrhage location on the current user ABOX individual, we can transition into the successor node, right? And all that successor node does is it uses a NLG template that peeks into the ABOX using pass expressions here to retrieve the hemorrhage location, and it simply confirms the recognized hemorrhage location, right? So it then says, okay, face hemorrhage, right? Using the pass expression into the ABOX individual. And then immediate transition is set. This means this node doesn't wait for user input, but it directly transitions into one of the specified successor nodes now in the next clause, right? And which of these nodes is the successor? Well, it depends on which node is enabled or applicable, right? And that depends on further conditions. So in this case, this node here asking can the wound edges be easily reapproximated is only enabled and applicable, and hence can be a valid node to transition into if the negated condition here evaluates to false, right? And what the condition specifies here is that the hemorrhage location on the current user individual must not be near to the eye, right? Because we are checking if we can apply one of those clamps, right? And that's not the case if the bleeding location is close or near to the eye. I wanted to give you a quick glimpse of the visual generated dialog workflow graphs. We are using graph, width, and dot, so they are being generated from the common Lisp macros. And I'm not going to explain them in detail here. If you're interested, please have a look at the paper and the references, so you can find these graphs online and have a look there if you're interested. So, what does DSL buy us in terms of modeling efficiency? We measured the reduced levels of effort, LOEs, for Onto VPA development for MEDIC and another larger VPA, SharedPal. So basically we are comparing Onto VPA modeling with and without DSL here by comparing level 3 to level 1 modeling. The numbers are of course not very representative, and this is a very coarse guesstimate, so take that with a grain of salt. But the overall finding is that the DSL has really paid off for us, and that the LOE reduction in modeling time is significant, like a 49% reduction for MEDIC and even a 83% reduction for SharedPal. We reached the end of my talk. To summarize and conclude, implementing a DSL is considerably less effort in Common Lisp compared to other environments. Its flexibility allowed us to maneuver in unknown terrains without getting stuck, and this is of course very important for research and prototyping. However, Lisp doesn't live in a vacuum, and it is not always easy to find solutions that are acceptable to both management and the customer. But Lisp has your back. Its flexibility allows you to find niches for it. There never really was a single DSL. The DSL has always been project and domain specific. I believe that the DSL creation overhead would have been a severe impediment in other environments, if I had to define parsers, meta-object models and what have you. But in Lisp, it makes life easier. Lisp allowed us to survive, to evolve and to adapt quickly. So yes, Lisp is alive, and using it in these projects was never the problem, but part of the solution. Thank you so much for listening, and hope to see you again at next year's ELS. Until then, bye, take care. Hello and welcome to my 2022 ELS presentation. My name is Michael Wessel. I'm an Hello everybody, nice to be here, albeit only virtually. Hope you can hear me. I'm Michael.
Hello, it's nice to have you here. I'm hoping for some nice questions from the chat because I don't know about you, but I'm busy processing your talk. It's been very information dense.
Yeah, I think maybe I put a little bit too material into it. But I really try to convey also the Lisp aspects, even though, as you heard, a large part of it was also about ontology modeling and OWL and other things. But I hope you found it somewhat interesting.
Yeah, I'm sure that on the third rewatch, there will actually be some understanding. On the first one, it's just, I am in awe. Thanks.
Like, at least from my point of view, can you hear me well?
Yes, I do.
Okay. Hello, Porto. Hi, Michael. At least I've commented on chat already. This, I think it's enough material in a way to be understood over course of hours. I think it reads like some sort of a war story from a prolonged project that uses CL and integrates it with some other technologies such as Java, and also, well, deals with customers. So that's already the business sort of thing. No questions come to mind since, well, this was a condensed presentation and a real lot to put in for half an hour. I will try to take a look at the paper afterwards and try to rewatch.
We have a question.
Yes.
Yeah. So we have a question from chat. What were the challenges in coming up with a DSL for SparkQL rising from using Common Lisp?
Well, actually, we don't have a DSL for Sparkle, right? So, and that was, yeah, I think one of the challenges. I mean, to find a dialog workflow graph representation that would allow the customer to do somewhat complex things, right? Sparkle is a very complex language. You can do many sophisticated things with that. That would not have that level of complexity. So it's certainly a little bit simplified, right? And it requires additional control vocabulary then in this DSL language, right? For example, to represent these kinds of conditions that I try to explain to check applicability of certain nodes, right? For example, is the bleeding close to the eye, right? And in Sparkle, you would just write that as part of the query, right? But you can't do this in this domain-specific language. And honestly, I mean, Sparkle is probably also too complex for the customer, right? So at least that was our experience. So we needed to come up with something which basically, yeah, makes it a bit simpler. And I mean, what we found there is just using vocabulary from the ontology, right? Which is, in a sense, the language of the customer, right? But then using basically pairs expressions and things like this, right? And so that way they were then able to basically use that language, right? With our help, not alone, right? But with examples, it was more accessible and doable for them than with Sparkle and OWL alone. So and certainly the main motivation for us was to have a more easily understandable model basically for the system, right? And yeah, also to have higher modeling efficiency for ourselves. So.
All right, thank you. So we have some questions from the live audience in Porto. Could we try to switch to that, Miguel?
Hello?
Hello, we can hear you.
Yep.
Hello, thank you for your talk. I'm really curious as a database developer of a graph store. as you mentioned Sparkle, our database is written in Common Lisp as well, dydra.com, and has a Sparkle endpoint. I'm curious what you are using here to what backend are you talking in Sparkle?
Yeah, so that was Apache Jena, in-memory Jena Sparkle engine, and Jena also has a couple of OWL reasoners, right? And I think it's around for many years by now. I think first versions of Jena were still funded by HP, right? And since 2000, I think Jena is around, and I must say that the rule engine and the performance of Sparkle, it's all in memory. It's pretty optimized by now, and it's I can say that their rule engine is better than what we have or had in Racer. So I must say that, yes, it's a good implementation. I mean, I had to do some fixes actually internally, but it is a high performance in memory implementation. And it offers a lot of expressivity. For example, we needed to have custom defined filter predicates in Java, right? And so it really offered the flexibility that we needed.
Okay, thank you. I have the second question from the online chat. For the demo, when the
Yeah, so the library was indeed the public library, and so it was a demo system. We only had like 50 or 60 points of interest, right? And what that query was meant to demonstrate, can you show the library on the map, right, was the use of basically identifying the reference to a previously discussed dialog entity, right? Since the library wasn't discussed previously, it didn't occur in the dialog history. So that was meant to illustrate that the system is reflexive in the sense that it knows what has been discussed and what has not been discussed, right? Because in order to deal with these anaphora, right, the library, right, or the Chinese restaurant, the Asian restaurant, it goes through the discourse, through the dialogue history, and tries to identify, okay, what is the user referring to, right? And in this case, there simply is no candidate for the expression the library, right? So it cannot figure out what, since it hasn't been presented yet, hasn't been discussed, it wasn't part of the dialogue yet. So that was actually a demo of a capability, so to speak. But I think it's confusing. Yes, thank you. So we should make a better demo for this.
Okay, thank you. I think we have one more question from the live audience. Miguel?
Yeah, can you hear me?
Yeah,
Yes.
I can hear you well.
Yeah. So I wanted to ask who are the users of the DSL, and what do they use to write it? So do they use Emacs or some other editor?
Yeah, I think, I mean, I must say they used all kinds of editors. So sometimes they even use words, right? Because, I mean, they are not really, you know, computer scientists or software engineers. So they are really more like on the, you know, domain level experts, so to speak, right? And so, yes, they need some help with that for sure, right? But also having a visual representation and a conceptually understandable model of workflow graphs, that is something they can understand and they can participate in that. So I think that was the main message. But yeah, it is not something that they can really use fully autonomously for themselves.
Okay, thank you. And it seems that this is the last question since we are out of time. So huge thank you for the talk and applause.
Thank you all. Hope to be there in person one year again. Bye-bye.
Bye.
Bye, thanks.